In 2019 and 2020, we dominated the router wide area network or WAN category in the Pwn2Own hacking competition. In this category, hackers attack network devices with previously unknown vulnerabilities from external networks such as the internet. Unfortunately, by 2021, our competitors reverse engineered our techniques and the game was up. Today, we are starting a video series where we'll show you our tips, tricks and techniques to find and exploit WAN vulnerabilities in network devices. And we're starting with a beautiful DNS exploit that got us $20,000 in prizes. Let's get ready to pwn. Hey, this is Pedro from the Flashback team. Most network devices have two or more physically and logically separated domains. These are the LAN, or Local Area Network, LAN, and the WAN, or Wide Area Network, WAN. Most of you will already be familiar with the LAN, Local Area Network. This is the internal trusted network in your homes, for example, or in your offices. This is where you connect all your devices, your computer, your mobile phone via WLAN or wireless LAN, your smart TV, your smart fridge, whatever. And because it is trusted, typically a network device such as a router will have a lot of network services listing on the LAN side. These are, for example, HTTP configuration, UPnP for configuration, some custom vendor services for mesh or any other type of stuff. The WAN, or Wide Area Network, is the port that connects your network device to the external world. This could be connection to your ISP, connection to the internet, etc. And the WAN, by default, is considered untrusted, and typically, network devices have very few or no services listening on the WAN. All these concepts apply also to enterprise network devices, but in a slightly different way. For example, enterprise network devices might have several WAN ports and might have several types of LANs, some more trusted than others. They might also expose more services on the WAN wide area network side. Most hacks you see published online are for the local area network LAN side. Wide area network or WAN side exploits are quite rare. But we already published one at least. The main reason for this is, as I explained before, the wide area network or WAN side usually exposes no or very few network services that us hackers can attack. In fact, modern consumer routers do not expose any services on the WAN. Everything's firewalled, so we cannot hack them, right? Let's talk about our target now. TP-Link Archer A7, also known as C7. This is a regular consumer router, which was a target for both the LAN and the WAN router categories in the Pwn2Own hacking competition in 2019. But you know what? We already talked about this router extensively in our first video titled How We Hacked a TP-Link Router and Took Home $55,000 in Pwn2Own. We highly recommend you watch at least the first part of that video, where the famous hacker king, Radek shows you how we got a debug root shell on the device via UART. If you watch the video as I just recommended, then you know how we got this debug root shell. Let's start our adventure by using netstat to determine what network services are listening on all interfaces. As you can see from the output, there are several network services listening on port 0.0.0.0, which means they are listening on all interfaces, including the WAN interface. However, this does not mean that we can access these services from the WAN, as the router's firewall might be blocking our way. Instead of doing the right thing, which is inspecting the router's IP table's firewall configuration, let's just skip it, wing it, and run the Nmap network scanner to see if we can reach any of these ports through the WAN interface of the router. We connect our computer to the router's WAN interface and assign it a static IP address to both the router and our computer. Our computer will be at 5.5.5.1 and the router at 5.5.5.50. Let's run our nmap scan. No results at all. All the ports appear to be closed from the one side. Hey Radek, what should we do about this?
Yo, Pedro, you give up too quickly. Just try harder. Okay, let me try before we move on to a different attack surface. First, I download our Suite package, statically compiled MIPS essential tools. Now I have access to all the tools that I need. Pedro checked already all the ports running with netstat, but let me have another look. Okay, what is this? A process conn-indicator running on some strange high port? You know what? Let's just fuzz it with my awesome fuzzer and see how it reacts. Yeah, that's my award-winning fuzzer. Okay, that was quick. Let's see if the process is still up. Wow, a segmentation fault. That means the process crashed and we might have a potential vulnerability in here. Indeed, the process is gone. I need to investigate it more. Let's start the conn-indicator binary again and attach a debugger to it. I will use GDB server to debug on the target. It exposes a debug port for me to attach to it. On my computer, I will use GDB multi-arch to connect to it. Pedro will be using some lame Jeff extension, but I'm a proper old school and gonna use plain and simple GDB. Okay, everything is up. Let's just fuzz it again. Is the port still the same? No, it changed. Interesting. I'll figure it out later, but now I need to adjust my command. Okay, let's go. Look at this, it crashed again at the address 44E44. Let's see the registers and get backtrace. No backtrace? Okay, I think that could be due to GDB, I don't know. So at this point we know we have a crash, but we don't know why. I think it's time for some reverse engineering of conn-indicator to find out what is this binary even doing. I open conn-indicator binary in Ghidra, a reverse engineering tool. Let's jump to that 44E44 address where we had segmentation fault. Okay, we have it. So what is going on here? It tries to get a value from address stored in register S2 and store 1 byte from there into register S1. S2 actually holds argument 1 of this function. We can see in the compile view a corresponding code. Indeed, it dereferences parameter 2 and stores it in a local variable. So why is it crashing? Let's have a quick look again at GDB register's value at the moment of segmentation fault. Okay, so S2 stores what it looks like a memory address. We can easily check to what memory addresses is this binary mapped and what memory addresses are used by shared libraries. Okay, so binary itself is on top and then COM libraries. So what was the address in S2? 7FFF0B06. Okay, so it is actually falling right between mapped stack and VDSO. That's why it's crashing. It tries to access a memory region that was not mapped, therefore not accessible. I think we nailed this one, so it's time to go back to Ghidra to understand more. Okay, so the function is actually calling itself as a recursion. There are some potential juicy copies here. And this function is called by tpdns receive and resolve function. That name is quite descriptive. Let's go there. Doesn't look easy to understand. Doing a lot of operations, calling other functions. Okay, reading from a socket we've received from. Very interesting. Wait a second, but the function is not being called by anybody? Okay, let's use the cross-reference view to find a place where this function address is being used. Okay, there it is. Okay, let's define this memory region as a function actually. That log string is very helpful. DNS responded CB, which probably is callback. Yeah, and look, it's called by DNS query init. Okay, some structure or a table of function pointers. And here another useful log string, DNS query initialized. Yeah, so I guess at this point it's quite clear we are dealing with DNS here. But to fully understand the internals and see if our crashes can be useful, I need to spend a few hours reversing. Bear with me. After a few hours of reversing, I finally know what is going on. Conn-indicator. It starts on boot, and its only job is to control the LED light on the router. The LED lights indicate if the internet cable is connected and if you have internet connection. That's it. It binds to ephemeral UDP port, which means that on each boot it will have a different high port. So how does it know if it is connected to the internet? Well, by sending DNS requests all the time. It has a list of predefined domains for which it sends queries. Let's take a look at it in Ghidra. Here is the domain list. It is used by three functions: query responded CB, detect net, and send query. And here is the array of domains. Look, there are just a few of them. You know what? Let's confirm this by sniffing on the wire. If my reverse engineering skills are good, we should see DNS packets, right? Let's do it. Here I opened Wireshark and sniffed on the interface connected to the target. And look at this. I was right. A lot of DNS requests coming from 5.5.5.50. tplink.com, ebay.com, amazon.com, and so on. Those are all the domains that we just saw in Ghidra in the domain list structure. So we are on the right path. Obviously, everybody knows what DNS is, that it resolves domain names to an IP address. But actually, to move forward, it is better to go a little deeper into internals of the DNS protocol. Let's do a quick recap. So here is our target. It sends a DNS request, and this is how it looks on the wire. We can ignore lower level headers and go straight into DNS packet. Okay, so DNS packet starts with a transaction ID. It is a unique number that is used to match request and response to each other. If a requester receives a packet with an invalid transaction ID, it must discard it. Then we have some flags, information how many questions are included in this request, and then information about answers, authority, and additional resources. After that comes the actual query domain. It is encoded using length and value schema. That means that preceding byte indicates how many bytes of value follow. In our case, the length field is hex 7, which means there are 7 bytes of data that follow. It is ASCII encoded TP-link. Next, 3 bytes of data follow, which is COM. It is terminated with a null byte, which means the end of the query string. So now we know the DNS request is for a tplink.com domain. So notice that we don't have any dots in the query. They're added automatically. Okay, that's it. Then the response packet arrives to the target. So we have a situation like this. A target sends the DNS request packet asking what is the IP address of a tplink.com domain. DNS server holds information about IP address and will reply with a DNS response packet and information about the IP address that has been assigned to this domain. Let's take a look at the internals of the response packet. This is the response packet as it was delivered on the wire. Again, we can ignore lower level network protocols and jump straight into the DNS response packet. It starts with a transaction ID that I mentioned before. It must match the transaction ID that was in the request. Then we have some flags to indicate that it's actually a response packet and about other properties. Next, This is information about how many questions were there and how many answers are included in this response packet. Some other fields we can ignore for now. This is interesting here. What follows next is the actual copy of the request domain that was sent in the request DNS. So it was a domain request for tplink.com. And finally come the response section with resolved IP addresses. We can take a look at the first answer and how it should be parsed according to RFC. First byte is especially important, so please make sure you understand what is going on. So the first byte indicates what mode is used to match domain to a resolved IP address. It takes a value of a first byte and performs a logical AND operation on it. This is used to check if two high bits, or in other words, two most significant bits, are set. In our case, yes, they are set as the result is positive. This means that a compression mode is used. What it exactly means, I will explain in a second. But let's see what happens if two most significant bits are not set. For example, like before when a tplink.com domain was used. We perform logical AND operation on the length, so that was hex 7, and the result is 0. That means a len value mode is used. Okay, I know it might be a little complicated, but it will be super crucial later. But what implications it has on the remaining data? Well, in our case, two most significant bits are set, thus compression mode is used. That means the next bytes are to be interpreted as a pointer value. As we already had a copy of the domain that we asked to resolve, we can simply match this record with the location in the DNS packet. The value is hex 0c, and it's an offset from the beginning of the DNS packet. So again, the response section contains IP address of a certain domain. And here, using compression mode, we know that an IP address will be for a tplink.com domain. We have properties of the answer for how long the answer is valid, and after that, length of the actual IP address, and finally, the IP address. At this point, we know that tplink.com domain resolves to an IP address of 34.232.217.36. Now, as we understand internals of DNS protocol a little better, let's go back to Ghidra and see how conn-indicator parses that data. As you remember, we have spent some good time reverse engineering the binary, and we have put a lot of comments and symbols, so it's easier to go through a DNS handlers. Let's start from the top of the tpdns receive and resolve function. We enter a loop where data is being read from a socket. It reads up to 2960 bytes and places that on the local buffer. This could actually be presented as a structure, but it is a little easier this way. Basically, our packet will be placed here. That creates a sort of a mapping of the local variables to the actual data in the DNS header like this. Each variable is of integer size, so it takes 32 bits. Specific fields can be accessed by referencing corresponding DNS resp variable, but remember to take NDNS into account. When it's done reading from a socket, it moves on to the actual packet parsing. It ensures some minimal data size was received. It performs a switch case on the rcode field, which is a 4-bit return code flag. 0 means all is good. Then it retrieves the number of query domains and continues to parse it in the DNS answer parser function. We can skip parsing domain name and go straight to answers that hold the IP address of the domain. I think that is more interesting. Obviously, in order to enter that branch, answer field must not be 0. Execution flow enters process resolved IP function. Okay, it has some interesting local buffers. It checks if all answers have been parsed already. If not, call DNS answer parser. It takes 4 arguments: pointer to the received DNS packet, pointer to the answer section of received DNS packet, a pointer to a local DNS query buff, and a static value of 1, which is some sort of a flag. Basically, at this point we have this situation. Target receives DNS data and it reads up to 2960 bytes in TP-DNS receive and resolve function and places it on the local stack. Then it calls process resolved IP function with a pointer to the DNS answer data that we control. It sets up its own stack and local variables and local stack buffers. Interesting ones are resolved IP and DNS query buff. Eventually, it calls DNS answer parser function with a pointer to the input data and a pointer to the stack buffer DNS query buff. Alright, let's dive deep into DNS answer parser because this is where the magic happens. This function basically parses received answers, taking into account a compression mode and length value mode. Let's skip this section for now. It will be easier to understand it in a while. Here, it is checking if 2 most significant bits are set in order to detect if a compression mode is used. Remember, it's this situation with that hex C0 logical operation. If compression mode is used, a following data is a pointer to the actual domain string. And here, function calls itself recursively, but it moves a data pointer by the offset. Now it starts from the beginning again, but this time the DNS answer pointer has changed. And if you paid attention, you would have noticed that this is actually where our initial crash happened, remember? So what happened was that we passed a huge offset value, and based on this, it calculated a new pointer, and instead of pointing to the actual DNS packet with a domain name, it pointed to an unmapped memory area and tried to read data from it. But we got a segmentation fault because we tried to read from unmapped memory addresses. Okay, but let's see what happens in other part of the function. Here it checks if .flag, our 4th parameter, is set to 0 or to 1. If you remember, it was 1, so we enter else function with that juicy memcopy. I think it's processing length value type of input here. So again, first byte defines size of the value that follows. Let's have a closer look. The source is DNS answer buffer that we control. Okay. The length is a byte from the same DNS answer that we also control. This is getting interesting. Where do we write that data? Into question buffer. Okay, it was passed to this function as an argument. Let's go to a caller to see what was the size of this buffer. Oh wow, it's 260 bytes and we send up to 2960 bytes of data. I think we have a winner here. Hell yeah. Okay, let's go back to DNS answer parser function and see if we have some limitations here. So in order to enter this branch and avoid parsing compression mode, we need to pass a byte value which is smaller or equal to hex 3f, so that 2 most significant bits are not set. However, this is not enough to overflow that buffer. But obviously, parsing loop will continue as long as we don't enter compression mode and as long as we don't send a null byte. And here, dots will be added automatically on each loop. So basically, we have a situation like this. DNS answer function processes our input. If two most significant bits are not set, it expects length string format. Our controlled input is processed in a loop as long as string is smaller than hex 40 bytes and it is not null terminated. On each iteration, extra dot is added, but there is no check if the buffer that we write to is large enough. We can send a sequence of length string, and so on, and that will write into the DNS query buffer and eventually overflow it. We will trash some other variables and write into a return address, which means we could take over of the program execution. At this point, there is nothing left but to write a POC and confirm our observations. If we can control instruction pointer, we are in business. This is our game plan. We need to construct a DNS packet that will avoid all unnecessary branches and, at the same time, hit the vulnerable one. In order to do that, the packet should look like this. Target receives our data. We need to set our code to 0 to enter relevant switch case. As you want to avoid domain parsing branch, let's set QD count to 0. We need to have at least one answer, so let's set AN count to 1. Okay, now we enter process resolved IP. We didn't parse any questions yet, so we're gonna go straight to DNS answer parser function. We take first byte from the DNS answer section. It cannot be 0, and it also cannot be a value larger than hex 3f, so we don't enter this compression mode part, but go straight to our beautiful mem copy. So our first byte is len. Let's have it set to hex 3f, followed by a corresponding size of A's. This will be written into our vulnerable buffer. On the next iteration, we execute this memcopy over here. As the vulnerable buffer DNS query buff is 260 bytes in size, we need to execute in a loop at least 5 times. The remaining fields don't play a role in the execution path. Sweet. With DNS answer data like this, we should be able to crash the conn-indicator and control the execution flow of the process. I smell blood here. Okay, I think that was pretty tiring, but I hope you understand at this point what we're after. Pedro, please take over the exploitation phase in the part 2 of this video. Make sure to watch it, and I hope we win.
All the content we put on our YouTube channel, all the advisories and exploits we release, that's all free and sponsored by our own training. Do you enjoy watching our videos, learning new hacking techniques, and finding and exploiting vulnerabilities? And why don't you come to our embedded device hacking course, which we regularly host all over the world, live in person. There are many hardware, embedded device hacking, IoT exploitation courses out there, but ours is truly unique. Why is that, Rado?
We focus only on real vulnerabilities that we or other hacker find. And as you can see from our videos, we have a lot of experience hacking real devices in Pwn2Own or our day jobs. The goal of the course is to teach you how to take apart embedded devices by analyzing the hardware, obtaining the firmware, reverse engineer it, find a vulnerability, and exploit it. Our mottos are no fake vulns and POC or GTFO. For more details, check our website and get your ticket now.